Welcome to The Explainer. Today, we are diving deep into a topic that, get this, makes up a whopping 25% of the CCNA exam. I'm talking about IP connectivity. Look, mastering this isn't just a nice to have, it's absolutely essential if you're serious about being a network pro. I mean, it really does feel like magic, right? You click a link and boom, a website from halfway across the planet just appears. But here's the thing, it's not magic at all. It's actually a super logical step-by-step process. So let's pull back the curtain and trace that journey together. And the best way to do that, to really get it, is to follow the journey of just one single data packet. We're going to see how it's born on your computer and how it finds its way to a server. And along the way, we'll uncover all the core concepts you absolutely have to nail for your CCNA. All right, first things first, our little packet can't go anywhere without an address. It's just like trying to mail a letter. No address, no delivery. In the digital world, that's what an IP address is. It's the packet's mailing address. So what exactly is an IPv4 address? Honestly, the best way to think about it is like a phone number, but for your computer. It's a totally unique number that lets every other device on the network find it and, have a conversation with it. Simple as that. But here's where it gets interesting. That address, 192.168.1.1, that's for us humans. It's easy for us to read. Computers, they don't see that at all. They see a long string of ones and zeros. See, the address is broken up into 4 parts called octets. Each one is 8 bits long, giving us 32 bits in total. That binary string at the bottom, that's what the computer is actually working with. Okay, pen and paper time, because this is a huge deal for the CCNA. You have to know that not all IP addresses are created equal. You've got public IPs and private IPs. Devices inside your house, your laptop, your phone, they all use private IPs. They can't be seen on the internet. To get online, your router uses one single public IP from your internet provider. It's like the one mailbox for the entire apartment building. So, our packet has its address. Awesome. But that address doesn't just identify the device. It also tells it what neighborhood it lives in. We call that neighborhood a subnet. And now we're going to see why carving up our network into these little neighborhoods is so incredibly important. Which, brings up a pretty good question. Why even bother with all this? Why not just dump every single device onto one giant, chaotic network? Wouldn't that be, easier? Well, the short answer is that would be a complete mess. A single giant network is slow, it's insecure, and it's a nightmare to manage. Subnetting is how we fix that. It cuts down on all the unnecessary chatter, it lets us wall off different parts of the network for security, and it just keeps things organized. It's the difference between a chaotic city and a city with well-planned neighborhoods. Okay, I cannot stress this enough. If you take one thing away today, let it be this. Subnetting is probably the single most important topic you will face on the CCNA. You will get questions on this. There's no way around it. So let's break down the logic step by step so you can handle anything they throw at you. All right, let's walk through an example together. Let's say we need to create 4 subnets. The magic formula is 2 to the power of n, needs to be at least 4. Well, 2 to the power of 2 is exactly 4. Perfect. So n is 2. That n tells us how many bits we need to borrow from the host part of the address. Our original mask was a /24, so we just add those 2 borrowed bits and we get our new mask, /26. See, it's just logic. And voila, here's what we just created. We took one big /24 network and turned it into these 4 neat, separate /26 subnets. Each one has its own network address, its own range of IPs you can actually use, and its own broadcast address. Total organization. By the way, that slash notation we've been using, like /26, that's called CIDR, classless interdomain routing. You've got to know that term. It's simply the modern way of saying exactly how many bits are in the network portion of the address. It's what gives us the flexibility to create subnets of pretty much any size we want. Okay, quick recap. Our packet has an address, so it has an identity. It belongs to a subnet, so it knows its local neighborhood. But what happens when it needs to leave its neighborhood and travel somewhere else? Well, for that, it needs a map. And that, my friends, is where routing comes in. So a router can get its map in 2 main ways. You've got static routing. Think of this as drawing the map by hand. You tell the router exactly where to go for every single destination. It's rigid. Then you have dynamic routing. This is like Google Maps. The routers all talk to each other and automatically figure out the best paths, even when things change. For small, simple networks, static is fine. For anything bigger, you need dynamic. And here is another absolutely critical CCNA concept, the default route. Think of it as the big sign at the edge of town that just says, everywhere else. If the router looks at its map and has no idea where to send a packet, it doesn't just drop it. It sends it to the default route, which is its gateway of last resort. And 99% of the time, that's pointing straight to the internet. Okay, the moment of truth. Our packet has arrived at a router. This is like a major highway intersection. And now, in a split second, that router has to look at its map and make a decision. Which way do I send this thing? And this right here, this is the router's brain. This is its routing table. You'll see this by typing show IP route on a Cisco device. So what are we looking at? The C means the network is directly connected. S means it's a static route we typed in ourselves. O means it learned the route dynamically using OSPF. And over on the right, it tells the router which next hop or doorway to send the packet through to get there. But hang on, look at those last two routes. They're both for a similar network, 192.168.3.0. So if a packet is going there, how does the router possibly choose? It's not a guess. It follows one single golden rule. And that rule is called the longest prefix match. This is so important. All it means is that the router will always choose the most specific route. And how does it know which one is most specific? It's the one with the longest subnet mask, the highest CIDR number. A /26 is more specific than a /24. So the /26 route wins every single time. So let's put it all together. Here's what happens in a blink of an eye. The router gets a packet. It scans its entire routing table for any routes that could possibly match the destination. Then it uses that golden rule, the longest prefix match, to pick the single best path. And finally, it forwards the packet out the correct interface to the next router, all in a millisecond. And there you have it. That's the entire journey, from start to finish. Our packet got an identity with its IPv4 address, it learned its neighborhood with a subnet, it got directions from the routing table, and the router made the final call using the longest prefix match. You now understand the fundamental flow of data across a network at a truly professional level. So, you now know how a single packet finds its way. But think about this. How do millions of them navigate this massive global map all at once without a single one ever getting lost? That's what we'll get into in our next explainer, when we look at the amazing services like DHCP and DNS that make all of this happen automatically.